All right, guys, welcome to part 2 of our math analysis video for March 27th. If you have not checked out part 1 of the video, watch that first and then come back here. So this is the equation that we, the function that we worked with earlier. You can see it zoomed out. It curves around, goes around there. It's kind of a light curve. Not as much of a curve as you want to see with a function when you're doing derivatives, but, you know, it'll be fine. So I have this graphed, and we are going to choose a point on the line. Now, what I want to do is I want to choose a point that it goes through perfectly, quote unquote, and that, for me here, is going to be point right here, 1, 7. There we go, 1, 7. So what I'm going to do is I am going to find the derivative of this function at x equals 1. So I'm going to write on the screen here. We have this point. Sorry, I'm not good writing with the mouse, but x equals 1 here. Now our original function was 2x to the third plus 5x, and we found the derivative to be 6x squared plus 5. So what I can do is I can plug 1 into this equation and try to solve for that. So I have 6 times 1 squared plus 5. Well, 1 squared is just 1, and 6 times 1 is 6. So 6 plus 5 is going to give me a value of 11. So the slope of this point of x equals 1 should be 11. Now, I've already done a few calculations prior to this video. Calculations that we're going to get into early next week regarding point slope form. But what we find is that using that slope of 11, if we were to write a slope-intercept form equation of it, it would look like this. Y equals 11x minus 4. I know you may be thinking, where did we get that minus 4 from? Don't worry, we're going to get into that. At this point in time, my main goal is just showing you that this slope of 11 is in fact tangent to that point and is in fact what we're working with. So you can see this was our point. It very much has that look of crossing through it, and then you can see that the line strays away from the other parts of our function here. If we can zoom out, you see it even a little bit better, where it continues to stay away from that line. Now we can even zoom in, and you can see that as we get closer and closer, you can see more and more of the gap between the purple line, the tangent line that we just graphed, and the red line of the function that we actually have. You can see those actually are farther and farther away. So I'm going to zoom back out here. So that is our first point of x equals 1. What I'm going to do is I'm going to choose a second point. I'm actually going to go to the other side of this graph, and we are going to choose x equals negative 1. Now we can see at x equals negative 1, it crosses all the way down here at negative 7. So if we plug negative 1 into this problem, let me erase all this. If we plug negative 1 into the problem right there, that looks awful, I apologize. There we go, somehow a little bit better. At the point x equals negative 1, then what we are going to say is that 6 times negative 1 squared plus 5. Yet again, we end up with 1 squared being, or negative 1 squared being 1, so 6 times 1 is just 6, and 6 plus 5 again gives us 11. So we actually have a matching slope at both of these points. Coincidental, maybe, but also maybe because of the fact that this line is symmetrical. So if we plug in a 11 for the slope of the point negative 1. Again, I already did a few extra calculations that we're going to get into later. We have y equals 11x plus 18. And that is not at all what I thought it was going to be. That is because that should be 4. Sorry, I did a calculation wrong that luckily I was able to figure out about really quickly. So we see this line straying off separately, ending up crossing with our point right here. If we zoom in, we can see it gets closer and closer and closer to that point, but it does only actually intersect at that one spot. And otherwise it stays tangent to the line at that point. The last one that I'm going to do right here is x equals 0, because we can find a tangent line at 0 as well. So I'm going to go ahead and work out the math on this one. So we see if our x value is 0, then when we plug this into the equation, 6 times 0 squared plus 5. Well, we know anything times 0 is 0, so our slope would just plain and simply be 5. I'm going to write an equation for it. Now we know if it is intersecting at this point right here, that must also be its y-intercept, or the y-intercept has to be at 0 because it's crossing through that point. So this is just y equals 5x. So you can see this line that I do kind of wish was in a different color, but it's the straight line here, crosses at this point at 0, but it actually ends up going on opposite sides of our original function here. I'm actually going to rewrite this in the hopes that it graphs in a different color. Nope, that's still red. There we go. So, like I was saying, you can see that it actually goes on separate sides of the original function, the red line, because our blue line here is tangent. If we zoom in, we can see that it really does only intersect at this one point, and it stays tangent to all the other parts of the line, no matter how far out we zoom. So again, that gives us our instantaneous direction and velocity, or our instantaneous direction, really. Velocity calculation is another matter. But that gives us our instantaneous direction and slope at that point x equals 0. Tomorrow, we are going to do, or I guess Monday, we are going to do one last example, and then we are going to try to look and see if there is a pattern amongst derivatives that's going to make finding these just a little bit easier. So thanks for watching, guys, and I'll see you next week.